All right, normally the tests are going to be 50 points. What that's going to mean are the multiple choice questions are going to be worth around 2 points. And then usually the free response questions are worth more. You know, quite a bit more. It depends on how many questions, but the tests are going to be similar. So tomorrow's test will be similar to this in terms of format, some multiple choice questions, maybe fewer free response. We'll see. It's going to be 1 page, and it might be more than 1 page. I might throw in an extra question in there that you'll do on the back of the sheet or on scratch paper. But let's take a look at number 1. For that equilibrium, increasing pressure of CO2 shifts the equilibrium to the left. This is Le Chatelier's principle. So if we increase the product, then there's going to be a shift to compensate for that. And so it's going to shift left to reestablish a new equilibrium. What if we increase the other product, calcium oxide? Will it shift left? Yeah. Yeah, it's a product, but there's something special about calcium oxide. It's a pure solid. So if we add some more calcium oxide, will that change its concentration or activity? No. And so pure solids and pure liquids are weird because they're going to have no impact. So even if we dump in a whole bunch of extra calcium oxide in there, it's not going to drive the reaction left. And the same thing goes for calcium carbonate. If I increase the amount of calcium carbonate, will it shift right? No, I just need some calcium carbonate in there, but it's going to have no impact. And so there'll be no shift for the other two. Whereas CO2, there will be a shift because that's going to change the concentration. It's also going to change the pressure. All right, number 2, actually, determine Kc for this. So this is kind of Hess's law. So the way I do this is I want 1 mole of hydrogen. I'll have 1 mole of hydrogen here, and none of the others give it. So I'll use this equation here. And then I want a half mole of O2. And I have a half mole of O2 here, so I combine these 2 equations. And that should work, except I have this graphite here that I need to get rid of. So if I combine these 2, I'm going to multiply the K's. So this case, that case. To get rid of the graphite, I'll flip this over. That's going to get rid of the graphite, and it's going to get rid of the CO2. And so it's going to be this times this divided by that, which should be this. So what you got? The units for Kc, in this case we have 1.5. So it'd be 1 molar, and then this would be 1 raised to the 1/2 power, so that would be 1.5. On the bottom, this would be 1 on the top. So you might say it's A, because we have 1 molar on the top and molar to the 1.5 power on the bottom. And it looks like it's A, but what we have to remember is with K's, do we ever include the units on K? We never include the units on the K expression. The reason is because they're dimensionless. There should be no units on the K expression because we really should be using activities. And activities have no dimensions. The units actually cancel out in the activities. And so the answer for this is D, none. There are no units in the Kc, there are no units in Kp, there's no units in the Keq. They're all dimensionless. For this reaction, Kc equals Keq. Is that true or false? Well, Keq's with the activities. And so it would be the activity of H2O gas divided by the activity of H2 gas divided by the activity of O2 gas raised to the 1/2 power of the square root. And when we look at the activities of gases, what do we use for the activity of gases? The activity of gases is the pressures. The pressures need not be 1 bar. 1 bar pressure, do you know where that comes from, 1 bar? Not STP. 1 bar pressure comes from It actually does come from STP, but for us, more importantly, 1 bar pressure is going to come from standard thermodynamic conditions. Under standard thermodynamic conditions. STP, you know how many times we're going to use that this semester? 0, yeah. But standard thermodynamic conditions, we're going to use a lot over and over again. So you need to know whether you're under standard thermodynamic conditions or not. And so that's important to that. But for this, KCs, we use molarity, the molar concentrations, and then we plug them into the KC expression. We drop all the units. KEQ, we use the pressure, either in atmospheres or in bar. And then we drop the units from that. So this is false. 5. The equilibrium here, delta N of gas. What is delta N of gas here? So we count out the moles of gas on the reactant side. So H2 gas, half O2 gas. So that's 1.5 moles. And then we go to H2O gas. So we're losing half a mole of gas. So we go from 1.5 to 1, and that's minus 0.5. That would be our delta N of gas. If delta N of gas is not equal to 0, then what's the significance of that? If delta N of gas is equal to 0 or not equal to 0, why do we care? Yeah, Kc is equal to Kp when delta N of gas is equal to 0. So in this case, we'd get a different numerical value for Kc versus Kp. And we could figure out the concentration, how many moles of gas are in a liter. 6, the activity of a pure gas is equal to 1. Its activity doesn't change. 7, activities should be used when solution concentrations and gas pressures become very low. Now, usually we use concentrations and pressures instead of activities because we're making the assumption that the gases in the solutions are behaving ideally. And the assumption that the gases in solutions are behaving ideally is best when the solutions are very dilute and gas pressures are very low. Because at high concentrations, then we're going to deviate from the stoichiometric concentration. The activities will deviate significantly from the stoichiometric concentrations. And so this is why when we look at all these calculations, they're always kind of small, the molarities. We'll look at it later. And so, no, this would be true if we were looking at very high gas pressures and very high concentrations of solutions, then it would be true. We need to use activities. But if it's very low and we can make an assumption that it's ideal or close enough to ideal, then it's false. We can just use the concentrations and pressures as is. To get the activities, we'd convert it. So we'd look at the stoichiometric concentration and then convert it to activity, which we aren't going to do. Compute the equilibrium molar concentration at pH 5. We did this one in class. Do you remember? So it's just solving for one unknown. Okay. If we look at that K, 9.1 times 10 to the 3, that favors what? Product or reactant or both? Products and reactants. Favors products. We'll have we should have a little bit of reactant left over, but primarily favors product. So that's why I circled it here. I was just looking at that number. Okay, next we're looking at 9 here. This is the equilibrium law. The equilibrium law is just some mathematical equation that describes the pattern. The equilibrium law originated from theoretical studies or from something else? Where did this law come from? And typically laws can come either from observation, those are called empirical laws, or theoretical studies, and those are theoretical laws. Where did this one come from? Observation, so this would be false. Number 10, hemoglobin. The hemoglobin oxygen equilibrium can be represented by this equation, Hb for hemoglobin, which has iron 2 in it, combining with 4 O2s to make this complex. Decreasing the temperature shifts the equilibrium. So decreasing temperature favors the endothermic or the exothermic direction? Exothermic. And increasing temperature favors the endothermic direction. So what we have to do is we have to figure out which direction is exothermic and which direction is endothermic. And so how can you tell? By looking at that equation. Bond formation and bond breakage. When we break bonds, does that cost energy or does that release energy when we break bonds? So if you were to break a stick, does it cost you any energy or the stick gave you energy? Like if you're breaking sticks, does it cost energy? And if it costs you energy, is that endothermic or exothermic? So breaking a stick, is that endothermic? It's going to cost you energy, or is it exothermic? You're going to gain energy from breaking the stick. Or how about this? Breaking hydrogen bonds, that is melting ice. Is melting ice endothermic, or is melting ice exothermic? Endothermic. So when we break things, it's endothermic. It costs us. However, when we form things, it releases energy. It's exothermic. So making bonds, why do bonds form? Because it becomes more stable. So when we make these bonds, it becomes more stable, it releases energy. And so it's going to be exothermic in the forward direction. However, to break those bonds is going to cost us energy. It's equal and opposite. And that's going to be endothermic in the reverse. So it's endothermic in the reverse, exothermic in the forward. So we're decreasing temperature, that's going to favor the exothermic direction, which is right here. So that's... should have figured that one out. All right, increasing volume. Shifts. Well, increasing volume favors the side with more moles of gas. More moles of gas requires greater volume. And so when we look at the total moles of gas on the left, we have a half mole, and plus a half mole gives us a total of 1 mole on the left. And over here we have 1 mole of gas on the right. All these are gases, and so there's no shift. It's not going to favor one side or the other. If K is equal to 612, equilibrium consists mostly of reactant. Well, you think, well, that's greater than 1, so it seems like it should favor mostly product. But really, it's not mostly product. It's just, it favors product a little bit.
But isn't that still more? Isn't it technically more?
If I said it consists of more product than reactant, yeah, then that would be okay. But mostly, you know, I know it's a bit ambiguous. But if you know, if, let's say, if you said, okay, 612 is bigger than 1, therefore it's a product. The thing is, how you know this is by doing some calculations and seeing what the numbers come out to, and then you can compare. And so this one, you could argue that too, you know, Gavin.
Yeah, because that's what I put. And I'm like, you know, maybe if it was like a really small K value, like K was like 2 or 3, but if it is like 612, it's like completely negligible, right?
Mm-hmm.
Is there like a number we should, like, or at least somewhere close that we could think of?
Yeah.
Where, like,
I mean, it's a gray area, but usually like 1,000, greater than 1,000, 1,000, 10,000, million, billion, trillion, then yeah, it's going to be more clear cut. In this case, it is a bit ambiguous, but normally when we look at a K value of 600, that's not so big. We'd say it's big, but not so big. But you could argue, that's more product than reactant, I'd take it. Yeah. So if that was your thinking, you can let me know. But both reactant, and there should be both reactant and product in significant quantities. And that's what we see when we do calculations, something like that. Okay, when a reaction is reversed, K changes sign. Is that true? No. So delta H would change sign, and delta U changes sign, energy changes sign, but equilibrium constants don't. What happens? Yeah, so K is going to be inverted. 14. For these take-home quizzes like this, ideally you should be able to get 100% on these. That would be your target. So for 14, for magnesium plus 2H plus yields magnesium 2 plus with hydrogen, either Kc or Kp can be used to describe the equilibrium. Kp definitely cannot be used. Kp cannot be used because the aqueous species, these aren't gases, so Kp. But what about Kc? Kc can be used for the aqueous species, no problem. But Kc can also be used for the gas. The problem with using Kc for the gas is it's not in the same volume. The aqueous solution is going to occupy this volume, but the gas is going to be above it in a separate volume. So what is the volume of that? And the concentration. And so that makes it more complex. And so it'd be more of a heterogeneous. You'd have two volumes associated with this and one volume associated with that, giving you different concentrations. Concentrations for the aqueous from a different reference point. But what would be best to use for this heterogeneous equilibrium? What would be best to use would be not Kc, not Kp, but Keq. Keq would be the best. And for Keq, we use molarities for the concentration and either atmospheres or bars for the pressure. And so the K expression would be a heterogeneous involving both molarities, molar concentrations, and bar atmosphere here. But you wouldn't have the units in there because K's are dimensionless. But you would base the K expression based on those units, so it's kind of weird. 15, the activity of pure water is approximately 1 over a wide range of pressures. That's true. Activity of pure solids and pure liquids is just taken as 1. (16) We have this reaction here. This is a reaction that you cover in biochemistry. This is a redox reaction. Citrate is our reducing agent, and NAD in this form is our oxidizing agent. That produces NAD conjugate. Reducing agent would be NADH or NAD reduced. And citrate's conjugate oxidizer would be CO2. Citrate's a reducer, and it's conjugate oxidizers. This would be NAD and oxoglutarate. You have to look at those together. But anyway, the K is 0.387. If we have a 0.387, then you might say it's reactant favored, right, because it's less than 1. But really the best answer is going to be a mixture of both because it is not so small. It's just 10 to the minus 1.
Like it's technically, like the other one says consists mostly of, and like it was kind of written like that, I could see, but technically the way it's written, it's which does it favor? And doesn't it technically favor the reactant? Just by a small amount.
By a small amount, yeah. And so this reaction favors by a very small amount, but when we're doing our calculations, it's for sure going to have a mixture of both. So the same thing happens here. And so we have to have some kind of reference point. And the reference point is going to be 10 to the third and 10 to the minus 3, then that's going to be our cutoff. But if you want to argue that, I mean, if you put reactant, then you're not wrong, It's just, for our purposes, this is the way we take it.
So that's technically where if I put a mixture of both, you could use things where you're like, well, it technically favors the reactant, so that's the correct answer. So
Okay,
I figured I'd put that one.
okay, that's fine. And so, make a note of that. You can tell me tomorrow
Okay.
during lab. And for others that did the same thing, you could do that as well. Okay, 17, vapor pressure of water is 23.8 millimeters mercury at 290 Kelvin. What is Kp? Okay, Kp is going to be based on what units we use here. In this case, atmospheres. If we use Kp in millimeters of mercury, we're done, because this is the equilibrium reaction here. The equilibrium, this is the vapor pressure equilibrium. And that's going to be the equilibrium between H2O liquid and its saturated gas volume here, which would be H2O gas. And so these are two separate volumes also, but this is in the space above the liquid. Nonetheless, when we look at it, K is going to be the activity of H2O gas divided by the activity of H2O liquid. The activity of H2O gas, we're just going to assume that it's the partial pressure of H2 gas. And the activity of H2O liquid is just 1. So here I have activity of H2O gas over 1. That's just, the activity of H2O gas is the partial pressure of H2O gas. Made a mistake here. I forgot the O. Let me put that in here. On H2O. There. So all we have to do is, here we have the equilibrium. The vapor pressure is the equilibrium, pressure of the gaseous form of the liquid in a saturated container here at 23.8 millimeters of mercury. So all we have to do is convert that into atmospheres using this. How many millimeters of mercury are there in one atmosphere? 760. So if you had forgotten that conversion factor, I probably would have given it to you in the test. 760 millimeters of mercury per atmosphere. That gives us that. All right, those are the multiple choice. So this is going to be worth about 2 points. And then we get to the free response. This free response question here is worth quite a lot, 8 points. So it's equivalent to 4 multiple choices. But you get partial credit here. For the multiple choice questions, you don't get partial credit. And so this one, we have lead metal is added to 0.500 molar chromium-3. Calculate the equilibrium concentrations. So initially I have some lead, so I just have to add lead present. But lead is a pure solid. Pure solids and pure liquids we ignore in the ice because the activities don't change in the ice table. And so that's why I drew a line through here. We have to have it there, because if we don't have any, then the chromium-3 has nothing to react with. So there's got to be at least a stoichiometric amount of lead or an excess amount of lead present. And then the chromium-3 attacks it, and so we start off with 0.500 molar here. And then here we have 0 molar and 0 molar. And so the first thing I think of when I set this up is the initial conditions. Should I reset them? And so that's the first thing I think of. Do I want to reset the initial conditions? Or should I go with what's given? These are the given initial conditions here. And so in order to determine that, I would look at K. When I look at K, 3.2 times 10 to the minus 10. 10 to the minus 10 favors what? The reactants or the... Yeah, this favors the reactants. This is going to heavily favor the reactants. So in this case, I'm not going to reset this because 10 to the minus 10 is going to favor the left. And it's already to the left. If this were 10 to the positive 10, do you know what I would do? I'd reset it all to the right. And so what I do is, I'd say lead is my excess reagent, and I'd say 2 chromiums would be my limiting reagent. So I'm going to completely consume all my limiting, and then this is 2, so this is also 2. So I'd have 0.500 molar here for the initial, and over here I'd have 0.250, half as much. And so if I reset this to the right, the conditions would be 0, 0.250, and 0.500. Do you see that? But I wouldn't do that.
Could you write it down?
Could I write it down? What?
The reset, if it was 10 to
Yeah, if K is big, you'd reset to the right. If K is small, reset it to the left. I could write it. Let me write it on the board. Wow. All the pens have disappeared. Well, here, I'll write it on this here. Maybe it'll be easier. I'll write it down here.
Professor, can we expect a similar multiple choice free response breakdown for the exam?
Yes. Similar. I might make more multiple choice and fewer free response exam, but I'll see tonight. I'll write it. Reset. If K is big, reset right. If K is small, reset left. The problem is what constitutes a big K and a small K. And so here, I would say this is pretty small. And so I'd reset this to the left, but it's already reset to the left. I don't have to worry about it. You see what we're doing is when we mix this together, the lead metal and the chromium-3 solution, it's immediately going to react. And so what we're doing is we're just backing up in time, to where we didn't have any reaction. You just mix it and then let them collide and react. So we start off with 0 and 0 here. Let's see what we do here. K is 0.387. If you're going to reset this one, which direction would you reset it? I'd probably, this one I'd probably reset it to the left. But when you have a 387, it's not really going to be as much benefit as it would be in the previous problem. And so one of the reasons we might reset this to the left is to get rid of binomials, because when we do a reset, we change the number of zeros. So for example, if this were already reset to the left and we have 0 here and 0 here, that means we only have one binomial here. This would be the binomial, and then we have an x here and a 2x term here. If we were to reset this to the right, then we end up with two binomials. Binomial here and binomial here. Those are going to take more time to solve, usually. And so there's another reason we might reset, and that's just to simplify the math by putting more zeros in the initial conditions. The more zeros you have in the initial conditions, the better. But when I look at this K value, it's not heavily biased towards the reactant. And so there's really no reason you have to reset this one here.
So it doesn't lose anything if you do decide to reset? Like,
No, it's fine. If you decide to reset, you could reset anything. It's not a problem. And you can reset it the wrong direction. It just makes the math harder if you reset it to the wrong direction. But it's not going to affect the final answer. You should still be able to get the same final answer. It's just going to be more work, usually. if I have something like this, 9.1 times 10 to the 3, I'd reset this to the right. You know. That wouldn't be a problem. For this particular problem, though, we didn't have to do it because they gave us the equilibrium concentration already, here, the H plus.
I have a question.
Mhm.
For number 17, if a question that is on the exam, is the conversion something we're supposed to know, or would it be on the exam?
If the conversion isn't on the exam, you can ask me for the conversion. Usually conversions I'll just write on the board. So if you forgot the conversion from millimeters of mercury to atmospheres, it's okay. You can ask me. I'll give it to you. Something like this, 0.64, maybe reset to the left or just leave it as is. You know, or even if you reset it to the right, you might reset this to the right. Depends. You know, if I reset this to the left and this came out to 0, that's better because then it's a squared term. So it'd be like 2x quantity squared, which would be 4x squared. Versus if I didn't reset it, then it would be a binomial, and then I'd have to multiply out the binomial by squaring it. And so a bit more hassle. In this case, you know, which way would you reset? Well, you might reset it to the right, but it doesn't really matter. In these particular instances, I'd look at the initial conditions and then I'd determine which way I'd reset it because it doesn't really bias towards one side or the other. Do you see that? And so my point would be to try to get more zeros here in initial to make the math easier. Uh-huh.
Sorry, one kind of question. Can you explain again how you why you I guess inverse the first equation to cancel out C? I don't understand that.
Okay, if we combine these two, you'll have one H2, that's what we want, and a half O2. But we have stuff we don't want. We have a carbon graphite here and a CO2. The carbon graphite and the CO2 aren't here, so we have to get rid of them. And so one way to get rid of them is to flip this, and then the graphite will cancel out the graphite, and the CO2 will cancel out the CO2.
Oh, okay.
And then that's what gives it a result. And so if we flip this, then we invert that, and then multiply everything together. In this one, we definitely want to reset it to the right. You know, if it isn't already reset to the right, I'd reset this to the right. That's going to make the change small. We want the change to be small, otherwise you're going to get something called round-off error with your calculator. And so that leads us back to this. This is good. We're just going to leave it as is. I'm not going to reset to the right because this is going to favor reactants. If it favors reactants, then we expect the change to be small. So 2x should be small, x should be small, and 2x should be small. And so we're going to have 0.500 minus 2x and x and 2x molar. And then we're going to solve for x. Actually, solving for x, we plug it into the K expression here. So on these free response questions, you should make sure to write the ice table in case these are the equilibrium concentrations here. So this is the final answer of that. In case you got the wrong concentrations here, so you get more partial credit, you have the ice table. And the K expression, if you have the K expression here written like this is KC. Then you'll get partial credit for that. A lot of people forget the square here. These are the coefficients here. Sometimes it's squared, cubed, whatever. But anyway, we're going to plug this in. X times 2x quantity squared. X times 2x quantity squared would be 4x squared times x is 4x cubed. So that's where this comes from, 4x cubed. And then the chromium-3 concentration is going to be 0.500 minus 2x. And lead, again, lead does not participate. So that's 0.500 minus 2x quantity squared. So we can get this into cubic form. And if you have a calculator, you don't have to make any assumptions. But even if you have a calculator, getting it in cubic form takes time because you have to multiply out this binomial. maybe it doesn't take that much time because this one's not so bad, but some of the binomials are terrible because they'll be like, rather than 0.5, they'll be like 0.491, you know, and then multiplying that out, this becomes a lot of key punching on the calculator. And so what I do is I'll automatically, I know the change should be small because this is biased towards reactant, so I'm automatically going to try the SA, you know, regardless of whether I think it works or not, I'll try. When I do the SA, what am I assuming? Not X, but the change. The change is really small compared to the initial. So in this case, the change is not X, the change is 2X. So what I'm saying in the simplifying assumption is I'm assuming that 2X is much, much smaller than the initial. The initial is 0.5, so that's supposed to be a 0.5 there. Looks like a 0.1. Okay. All right, if that's the case, then this simplifies to this. This is just going to be 4x cubed divided by 0.5 squared. And then solve for x. When I solve this for x, this is going to equal k. What was the k value? 3.2 times 10 to the minus 10. X comes out to 2.71 times 10 to the minus 4. All right, I went ahead and made that assumption not knowing if it's going to work or not, and so I have to justify it. And the way we justify it is if the percent change is small, then it's okay, but if the percent change is large, then it's probably not okay. So we calculate the percent change, which is going to equal the change. The change here is 2x, not x, divided by the initial 0.5. So 2x divided by 0.5 times 100% gives us 0.108%. And since 0.108% is less than 5%, then this is okay. And so I give it a little check. So the simplifying assumption works, and so x is equal to 2.71 times 10 to the minus 4. We're allowed 2 sig figs, but I usually carry extra, at least one extra, to minimize rounding error. And so the lead concentration is x, so that's 2.71 times 10 to the minus 4, or 0.000271 molar. The chromium concentration is double it, so 2 times that is 0.000542 molar. And then the chromium-3 concentration is 0.500 minus 2x, which is the 000542, which gives me 0.499458. And the reason I'm going to carry extra digits here is because I want to check my equilibrium concentrations. I'm going to check my equilibrium concentrations by plugging these back in the K expression. And so here it's going to equal 0.00271 times 0.000542 squared divided by 0.499958 or 499458 squared. And this gives me 3.191 times 10 to the minus 10. And the actual K value, the given K value is 3.2. So if we round this to 2 sig figs, it rounded 3.2, so we're okay. And so this checks out. And what you want to do is you want to double check your equilibrium concentration because sometimes you just make an algebra mistake. If you make an algebra mistake, it's easy to correct. You just go back and redo all your calculations. That's it. But make sure you double check this, so that you know. And I double check it before rounding it because when you round it, then you're going to introduce rounding error. And that rounding error can throw off the K value that you do. And so the final thing that we're going to do is we're going to round this to the correct number of sig figs. We're allowed 2 sig figs here. So what does this round to 2 sig figs? Just 0.50 molar. And then up here we're allowed 2 sig figs. So this is just going to be 0.00027 molar. And this will be 0.00054 molar. And so that would be the final answer here. But if I plug these in, that could throw this off further. If that throws this off further, then I don't know, is that due to rounding or is that due to a calculation error I did earlier? And so I don't want to redo all my calculations, so this is why I'm trying to carry extra digits so I don't have to redo the calculations if the K value comes off. All right, any questions on this problem? This problem we did in class, and so I just wanted you to do it the same way we did in class, and there's a reason I did it that way in class. So for example, here, normally if we go to amide, amide is the conjugate base of ammonia as an acid. If we look at ammonia as an acid, what is the Ka for ammonia? Very small. And because of the seesaw relationship, the Kb for amide should be very large. Yeah, very large. So normally the Ka value is very large. If I gave you a K value of very large, then you don't have a very large key on your calculator, so you wouldn't be able to do a calculation. But if somebody goes to the extent of actually digging up the K value and estimating it as 10 to the 20th, which is not anywhere close to infinity, is that close to infinity? No, because in order to have complete reaction, we need K to be infinity. Right? And so what that means is that, yeah, for the most part, this is all product, but there's going to be a little bit of reactant left over. And so in Chem 1B, we want to know what that little bit of reactant left over is. And so what some people did is they remembered, well, you know, strong bases hydrolyze water 100%. That's the electrolyte property of strong bases. Strong bases, strong acids, and soluble salts ionize or hydrolyze 100%. And so you aren't entirely wrong doing that, but in this case I wanted you to do some calculations here. And so the first thing is we have 0.100 molar amide and 0 molar here. And so the first thing I ask is, should I reset the initial values? What would you say? Yes. It's not to say that you can't do this. You can do this without resetting the initial values. But the problem is it depends on what you use to compute your x. If you didn't reset this, then your calculator is going to round x to 0.100. And so we'll go 0.100 minus 0.100 gives us 0. But that's not what I want. It's not really 0 here. Based on our calculation we did earlier, it's actually 1 times 10 to the minus 22 molar. And so how can you figure out it's actually 1 times 10 to the minus 22 molar? The way we figure that out is by resetting it so we don't have the rounding problem. And so that's another reason for resetting this. And if we reset this, that means the change will be small. And so what a lot of people got was they got this. They got equilibrium conditions of 0, 0.100, and 0.100. Well, that looks like my reset initial conditions. That would be my starting point. That would not be my equilibrium because the K value, does the K check out? So if I plug in these equilibrium concentrations into my K expression, I'm going to get 0.100 squared divided by 0, which is going to be infinity. Right? And so the K value is way off. And so what some people got as the equilibrium, I think that of that is my initial, my reset initial conditions, and then solve for the equilibrium. So we did that in class. So the K value comes out to infinity or approaches infinity, which is way off. Way off. It's not 0, it's 10 to the minus 22 molar, would be much more accurate. Well, 10 to the minus 22 is still very, very little. All right, the other thing is this. The other thing is, you know, you handle calculations differently depending on what I ask. So for some problems, I ask for percent reaction. So I might handle those problems differently than ones that ask just for pH. So if the problem just asks for pH, then I'm focusing on one thing, and I might be able to take shortcuts and skip things, make the calculation faster. Other times I'm asking for everything. And so if I ask for the equilibrium concentrations, not estimate the percent error, or the percent reaction, that's different than determine the equilibrium concentrations of the species. And so we should be able to do everything, and doing everything means we have to do this reset business. All right, any questions on this, 19? So those I made 8 points, and then I gave a bonus. This is the bonus question here I gave. I'll give you a bonus question on this. Test likely 2. So in this particular reaction, which is carbon monoxide plus hydrogen, this is a redox reaction producing methanol here. Kp is equal to 0.00923. So this is going to favor, this is like 10 to the minus 3, 10 to the minus 2. It's going to favor reactants. If it favors reactants, I'd look at my initial conditions, and my initial conditions are all reactants anyway to begin with. And so there's no reason to reset this. I just leave it as is. All right, so the next step is we'll just generate the ice table, minus x minus 2x plus x. So we get 10 minus x, 10 minus 2x, and then x. And then we solve for x by plugging into the Kp expression here. This is all in atmospheres. It could also be in bars, but this one was done in atmospheres. So we end up with this, and this turns out to be a cubic. So one option is to get this into cubic form. Ax cubed plus bx squared plus cx plus d. And plug in a, b, c, d into your calculator. And that way we don't have to make any assumptions. But you can't always rely on that, because what if I gave you a fourth order or fifth order equation or sixth order? If I gave you a sixth order equation, your calculator, if it's non-programmable, is not going to be able to solve it. And so we should learn other tricks to solving these. You might go, I don't want to do simplifying assumption. I don't want to do successive approximations. I just want to work through the math and figure out what x is without doing any of that stuff. But the problem is that you might not be able to figure out what the answer is through a brute force algebra approach. And so this is why we do tricks like simplifying assumption. Simplifying assumption doesn't take much time. And so I do this for everything. And in this case, we say the change is smaller than the initial. So here, x would be smaller than 10, or 2x would be small, actually both. And so what we're going to do is we're going to take the bigger change. X versus 2x. 2x is twice as big of a change relative to the initial. The initials on both of these are the same. Sometimes the initials are different, so we have to weigh them differently. But in this case, I want to take the bigger change. And so the simplifying assumption is saying the bigger change is smaller than the initial. There. And therefore, the smaller change is going to be valid as well in terms of it's going to be smaller than the initial here. So 10 minus x simplifies to 10, 10 minus 2x simplifies to 10. And then solve this for x. X is 9.23. And then we calculate the percent change. The percent change is 2x, which is our change here, the bigger one, not the smaller one. So we do 2x divided by 10. Sometimes people accidentally do the smaller one, and it comes below 5%, whereas the bigger one comes above 5%, but they just should always pick the bigger change. But anyway, the percent change is going to be the change, 2x, over the initial 10 times 100. It gives us 184, 185% change. 185% change is too big. And so the essay fails. The essay fails. So you have two choices here. One, you could get the equation in cubic form and use a solver. Or two, what can you do? Guess and check. Yeah, guess and check. Some people say, well, I have the calculator, it has a solver, I don't need to do the guess and check method. But the problem is the solver only goes to cubic equations, cubic third order polynomials. And so you need to use this method because sometimes we're going to get higher orders, fourth order, fifth order, sixth order, they're common. And so we're going to use a method of successive approximations to do this. Now, the first thing we do in the method of successive approximations is we determine the limits on x. X can range from 0, but it can't go below 0. It can't go negative. So x can go from 0 to 5, the max. Because here, our big change here, 2 times 5 is 10, so 10 minus 10 gives us 0. We can't go negative, so that's it. The range for x is bigger in this polynomial, this binomial here, than this. And so we pick the smaller range. K is kind of small. It's 0.00923. This is our target here. Now, when I do the method of successive approximations, I don't bother getting this into cubic form. It just takes too much time to multiply out all these binomials. It's not even worth it. So I just leave it in this form to save time. And this looks like it favors the reactants, so we expect the change to be kind of on the smaller side of 0 to 5. And so on the smaller side of 0 to 5, I picked 1. Why 1? Because algebra is going to be easier for this. This is going to be 10 minus 1 is 9. 10 minus 2 times 1 is 8. Square that. Invert it. And so this comes out to 0.00173. We need 0.009. That's our target. 0.009. So it's too small. Too small here. So I'll go bigger. X equals 2. So that gives us this. That gives us 0.0069. So we're about 0.07. We're getting closer. Getting closer, but still too small. Then I'll try x equals 3. I like to stay with these single digits here because that limits the. Once I go like 3.1, 3.2, then the math gets more complex. And so this is 1 divided by 7 divided by 4 squared, which is 0.026. So now we're way too big. We want 0.09. So we're between 7 and 27 here. Between 7 and 27, it should be closer to 2 than 3. So now we're going to have to split between the 2 and the 3 here. And so that means I have to add another digit. And so I thought it was a lot closer to 7 because 9 is a lot closer to 7 than 27. And so I went 2.1 here, right on 2 almost. And so with an x of 2.1, I calculated a k value of 0.079. It's 0.08. It's still too small, but getting close. Getting very close. So I went 2.2 here. 2.2 gives us 899, and so we're just about at 9.09. And then I went to 2.3, but 2.3 gets me 10. And so we're between 9 and 10 here. And so it's somewhere in there, between 9 and 10. Between 9 and 10, so I kind of went halfway between it. But I went closer to 9 here because it's 9.2, I think it is. Our target is 9.2, yeah. And so it's closer to 2.2. So I went closer to 2.2. I went 2.24, but kind of in the middle because it's not totally linear. So at 2.24, I get 0.0947. It's too big. So then I went to 2.23, which gave me 0.00935. That's still too big, but I'm very close now. Because I need 9.2, not 9.3 and 9.4. And then this just happened to work out lucky. Sometimes it's not so lucky. You go to 2.22 and it comes right on. We got 0.009230 right on there. And we got lucky. And so we could stop here because that's what we want. 0.00923, that's good. So our target was 923 and what we got is 923. Sometimes it's not. Sometimes we have to keep going, keep going, keep going. When you stop, let's say you're having a hard time converging on your target. When you can stop is when it's close enough. When it's close enough is either the K number here rounds to the target. Let's say we're at 9229. Well, 9229 will round to 923, so that's close enough. Or we have too many digits here. Let's say you're starting to get this is 3, 4, 5, 6, 7. Most of the digits are going to be rounded off anyway. And so, if you start getting way too many digits here in your X value, it's time to say you're close enough. Or if the K value rounds to what your target is, then you're close enough. And so how many guesses was this? That's 4, 5, 6, 7, 8, 9 guesses. 9 guesses is not bad. Some people can guess in fewer, but some people take more. One time I had a problem like this, and I had a student turn it in with 3 pages of guesses and didn't get the answer after 3 pages of guessing and checking. So sometimes you can get caught, spending or wasting a lot of time in a certain region and not getting closer. All right, so 2.22 is what we got. And so the methanol pressure, this will be in atmospheres. The methanol pressure is going to be 2.22, that's just X. The hydrogen will be 10 minus 2X. So 10 minus 2 times 2.22, which is 4.44. That's going to give us 5.56 atmospheres. And then the carbon monoxide pressure is going to be 10 minus 2.22 or 10 minus X, which is 7.78. And so these are the equilibrium pressures. And then what we're going to do is we're going to check our equilibrium pressures by plugging those back into the K expression. And so that's what we did here. We plug in the equilibrium back into the K expression. So that's the methanol divided by the carbon monoxide divided by the hydrogen pressure squared. Punch that in the calculator and see what it comes out to. And so this didn't quite work. The formatting got screwed up here. So if we plug this back in, we're going to get 0.009230 And so our target is 0.00923. So this is good. This checks out. This is good. Not the 0.04. The calculation is good. So let me just get rid of this check mark here. All right, how many sig figs are we allowed in this? It looks like we're going to have 3. And so this is 3. Normally I carry more, but it worked out. If your check here is coming off, let's say it's coming off and it's kind of far away from our target. The first thing I look at for is round off error. So first thing I check is maybe carry extra digits in the equilibrium. That might solve it. If that fixes it and we get closer, then we're good. If it doesn't fix it and we're still far away, then I'll go back and check all my calculations. All right, any questions on this? Uh-huh.
For the quizzes in general, is every single question worth the same amount of time?
No.
Than
In the quiz, yeah.
Oh,
For quizzes, yes. For exams, no.
okay.
Yeah. For quizzes, I just made everything the same because the whole thing's only worth 5 points. And we're going to have like 1,000 points at the end or so. But what I'm probably going to do is I'm probably going to drop your lowest quiz score. So I think we'll probably end up with more than 10 quizzes. We'll see. Mm-hmm.
For question 11, I kind of said that it went to the left just because I thought that like increase in volume meant like a decrease in pressure.
Increase in volume does mean a decrease in pressure. That's correct. If we increase the volume, we're going to cut the pressure. So if we double the volume, according to the ideal gas law, we cut the pressures in half. But the situation is we cut this pressure in half, this pressure in half, and this pressure in half. All of them are going to cut in half. So if we cut all the pressures in half, then what that's going to do is it's going to cancel out because of just the way it is. If we cut the pressures in half, then we're going to have 1/2 the pressures and 1/2 the pressures. All those 1/2s will cancel out. And then we end up with the same thing. Okay, any other questions on this? Uh-huh. Will the answer key be posted online? I was thinking I'll post this, but this is actually an old exam of mine, so the points, it's not the same. I mean, the questions are exactly the same, but the points are not. If you want me to post this, I'll post this.
Yeah, that would be helpful for like studying.
All right, I'll post this online. Let me save this. I'm going to call this Quiz 3 key, but it's not going to look exactly like your Quiz 3 since I'm just repurposing this old test. This will be spring of 26. Spring of 25, sorry, not 26. All right. Any other questions from chapter 16? Uh-huh.
Do you mind doing volume 17? Because I was trying to use like KP is equal to KC times RT to the power of delta N.
Number 17. Okay, we could take a look at number 17. This is back from Chem 1A. Back in Chem 1A, the vapor pressure is the equilibrium between the liquid and its gaseous vapor here. And so back in the liquids and solids chapter, you had something like this, where we need a closed container. So this is going to be a closed system. A closed system, no matter can escape out of it. And so we need a lid here. Otherwise, all the water can potentially evaporate off. What are the 3 types of systems that we deal with?
Closed systems, open system, and isolated system.
Yeah, closed, open, and isolated system. So this would be an example of a closed system in which energy and work, or heat and work can be exchanged, but matter cannot. And so what's going to happen is it's going to evaporate and it's going to create water. As the water accumulates in the gaseous phase, it's going to start to condense. And as the condensation rate increases, we'll hit a point where the vaporization rate is equal to the condensation rate, and we've hit a state of dynamic equilibrium. So the dynamic equilibrium is going to have the forward rate and the reverse rate equal. At 298 Kelvin, this favors the reactant, which is H2O liquid. It should be the dominant phase. We can do a Kc or Kp. The Kc would be the moles of gaseous water vapor in this airspace here. That would be the Kc. We just calculate the molarity of the gas. And therefore we could use Kc. But they didn't give us Kc, they gave us Kp. So for Kp, what we do is we just want to know the partial pressure of the H2O gas. The H2O gas is going to be colliding with the walls of the container, generating pressure with one another. So these are the collisions here. And they tell us the partial pressure because at 25 degrees C, the pressure is 23.8 millimeters of mercury. So that's Kp is equal to the activity of H2O gas divided by the activity of H2O liquid. Activity of H2O liquid is 1, so this is just equal to the activity of H2O gas, which is just equal to the pressure of H2O gas. So they give us the pressure of H2O gas is 23.8. We drop the units. But the units, we have to, it's weird because Ks are dimensionless, there are no units, but we have to keep track of the units because the K value is going to change depending on the units. So this is in torr or millimeters of mercury, but we don't include it there. This is millimeters of mercury or torr, which is equivalent to 23.8 millimeters of mercury divided by, or we'll just do this, 1 atmosphere is equivalent to 760 millimeters of mercury. So we can express our kV value in terms of atmospheres too. And so all we do here is just cancel out the millimeters of mercury, and then we end up with atmospheres. But then we drop the units again. And so here it comes out to 3.13 times 10 to the minus 2. 3.13 times 10 to the minus 2, or 0.00, oh no, not 00, 0.03. What did I do? 0.0313. Yeah. And we get rid of the atmospheres. So if you base Kp on millimeters of mercury, you end up with 23.8. However, if you base Kp on atmospheres, you end up with 0.0313. Uh-huh.
So because the reactant is a liquid, if this is just a matter of like conversion, like converting.
No, it doesn't matter. The liquid we completely ignore. Pure liquids and pure solids just completely ignore those.
Like yeah, but because of that, like it's only about converting the Kp into like the what was the atmospheres? So like 760.
Yeah, because of this the question asks what is Kp in units of atmospheres. And so it's given. So we would have to convert it. If I ask you what is Kp in units of millimeters of mercury, you're done. It's 23.8. If I asked you what is Kp in bar, what would you do? You'd convert from millimeters of mercury to bar. Do you know the conversion?
This one was ATM, so you could do it.
You could do it this way. I know it. I don't know if you know it, but you could always ask. It's 101.325 bar per atmosphere. Do you remember this conversion factor? Yeah. 101.325 bar per atmosphere.
And then it was torr and millimeters mercury that were interchangeable.
Yeah, the torr and millimeters of mercury are the same. So if I wanted this in bar, I'd do two-step calculation. I go from millimeters of mercury to atmospheres and then atmospheres to bar because I don't have the millimeters of mercury to bar conversion memorized. And I don't need to have it memorized because I can figure out another route so that I can minimize the amount of memorization I have to do. Okay, what time do we go till today? 50? 5. Okay, so we only have 2 minutes left. Other questions? Uh-huh.
For the exam tomorrow, could we use a graph calculator or is it just?
No.
Okay.
Graphing calculators, unfortunately, are not allowed. So you just have to use your standard calculator, your backup calculator. Uh-huh.
When you're doing guess and shit, do you always have to put every single guess that you did, or can you just type it into your calculator until you get the right answer?
You could type it in your calculator until you get the right answer, but you have to write something that you typed it in your calculator to get the right answer. Otherwise, I might think, how did you get that answer? You know, I need to see some guesses. So you might say, okay, guess from here to here or something like that and try a bunch. But, you know, to save time, you don't show it all. The reason you might show it all is if you don't get the final answer and it doesn't check out when you check the equilibrium concentration, so you get more partial credit. All right, good luck for tomorrow then.